The empirically determined rate law gives us a mathematical expression for the rate of the reaction. Let's see if we can start with our microscopic picture of the reaction and develop a similar mathematical model for the reaction. If the experimentally determined expression for the rate of reaction and our first principles expression developed from the microscopic picture match each other, then we know that we have included all of the important features in our microscopic picture. This will allow us to develop an understanding of why the empirical reaction rate takes the form that it does. In general, we want to model things from first principles because we want to understand the mathematical form that we obtain experimentally. Remember that our microscopic picture requires that the molecules collide with enough energy and in the correct orientation. Let's start with the enough energy part of this. Our molecules must have enough energy, that is, they must collide with an energy that is at least equal to the activation energy of the reaction, so that they will have a total energy available to them which is at least as large as the potential energy hill that they need to climb. Our Boltzmann distribution tells us that the probability that a particular energy occurs is the Boltzmann factor, e to the minus that energy divided by RT, divided by the partition function for the system. We can determine what Q is by remembering that this probability distribution must be normalized. That is, if I sum all of the probabilities over all possible energies from 0 to infinity, I must get 1. Doing this integral, solving for Q, we can see that my partition function must be equal to RT. Now that I have an expression for my probability of a given energy, I can find out what the fraction of collisions are that will have energy larger than the activation energy. In other words, how many collisions will have enough energy to overcome the activation barrier. The fraction with an energy larger than the activation energy will be equal to the sum, or the integral, over all probabilities from the activation energy to infinity. When I do this integration, I find that this fraction is e raised to the minus activation energy divided by RT. Based on my microscopic picture, if I take the number of collisions per unit volume per time, and I multiply that by the fraction or the percentage that have enough energy to react, and then multiply that by the percentage or the fraction that have the right orientation to react, I should find the number of collisions with enough energy and the right orientation that occur per unit volume per time. This will be equal to my reaction rate because it will tell me the number of collisions per unit volume, or the concentration per unit time, that actually react. The collision density is ZAB. The percentage with enough energy to react is equal to e to the minus e sub a over RT, and we will use P as the percentage that have the right orientation to react. Substituting in for our collision density, we end up with the following equation for the rate of reaction. Notice that we've written the steric factor P here, and the energy factor shows up here, and the rest of this is the collision density. Avogadro's number times the collisional cross-section times the relative velocity times the concentration of the two reacting molecules. In deriving this equation, we have assumed that A plus B collide to form products. So we have assumed that the elementary reaction is A colliding with B, in which case the experimentally determined rate law should be equal to K times the concentration of A times the concentration of B. Keeping this in mind, we can see that the rate constant, or rate coefficient, can be associated with everything that multiplies the power law in the reactants. And so my simple collision theory rate constant is equal to a steric factor times the collisional density divided by the reactant concentrations times the fraction that have enough energy to react. So far, so good. The rate of reaction using this simple theory reproduces the concentration dependence of the empirical rate law. What about the temperature dependence? The empirically determined temperature dependence, or the Arrhenius rate law, tells us that the rate constant is proportional to e to the minus activation energy divided by RT. We find that our collision theory rate constant also has this same kind of temperature dependence. In addition, we've now learned that this exponential temperature dependence arises from the fact that the fraction of collisions with enough energy that have energy above E sub A is exponential in 1 over T. If we look a little bit more closely, we can see that the Arrhenius pre-exponential factor can be associated with the collision rate and the steric contribution. Here we find a slight discrepancy with our empirical expression for the rate coefficient. Whereas empirically we find that A is a constant, here we can see that the collision rate does depend on the temperature, and so we would expect this Arrhenius pre-exponential to be slightly temperature dependent. Although this may seem like a large flaw, we find that the temperature dependence of the exponential part is so much greater than this t to the 1/2 dependence that for small temperature ranges, this pre-exponential factor appears to be constant compared to the large temperature dependence in the exponential part. Indeed, we find that if we are able to measure the rate constant over a wide enough temperature range, that we will begin to see curvature in our traditional Arrhenius plot. However, for small temperature ranges, we can approximate the plot as linear.